Okay, welcome to the online causal inference seminar. Today we are excited to have Kosuke Imai from Harvard University, who will talk about the Cram method for efficient simultaneous learning and evaluation. After that, we'll have a discussion by Rui Song from North Carolina State University. We have several collaborators in chat today in Q&A who will help with answering questions. Michael Lee, who is a collaborator of Kosuke, and Hengrui Chai, who's a collaborator of Rui. So if you have any questions, please submit them via Q&A. We also have Ying moderating the discussion, so I'll switch over to her now.
Thank you, Dominic. So I will be reading questions to Kosuke during the talk. So if you have any questions, please submit it through the Q&A section for us to better track the questions. If you raise a quick clarification question, I will raise it to Kosuke, and otherwise, I think most of them will be tackled by Michael. And without further ado, please feel free to take over, Kosuke.
Okay, let me see if I can share screen properly. Does it look okay? Okay, yeah, thanks for having me. I wanted to thank In for invitation, and Dominic and George and others who have been doing a great service to the world, that putting together this seminar series. It's been I've been a big fan of it, so it's an honor for me to be part of this. So today I wanted to present the paper that we actually just finished, and we're still trying to understand what we've done. So this is a great, chance for us to get some feedback. This is joint work with Zay and Jeff, who is a graduate student, PhD student in the statistics department at Harvard, and Michael Reeve, who is actually here, which is awesome. And Michael and I have been working on this issue of how you learn and evaluate the data-driven rules from in an efficient way. And so this is sort of the continuation of that work we've been doing for the last several years. Okay, so let me begin. So I want to first sort of motivate where this project come from. Okay, so I mean, we all know that the reason why we are important is because in today's society we've seen widespread use of data-driven algorithms for decision and predictions. Okay. In this case, in practice, what we really want to do is using the same data to both learn the decision or prediction rule from the data, and also evaluate the learned rule. Okay, so the second part, I think, is sometimes overlooked. I think we've focused a lot on how to efficiently learn the decision or prediction rule, but may have not spent equal amount of energy on evaluating the learned rule. And this is the learned rule is important. It's a rule that you actually learn from the data. Okay? And I'll try to sort of make this distinction as opposed to evaluating the algorithm. Okay? So as a methodologist, a statistician, we always like to evaluate our own algorithms. But what's important in practice is to evaluate the performance of the rule that you actually learned, and you're going to put it into practice. Right. So before you deploy such a rule, you want to evaluate how well it would do. So for this purpose, one strategy that's common is sample splitting. So by sample splitting, I just mean that you have a data set and you split that into training and holdout data, and you use a machine learning algorithm and they do some learning of the decision or prediction rule. And then once you have that rule, then you evaluate using a separate data set, holdout data. And then once you're satisfied with the performance, then you put that rule in deployment. You deploy that in the real world. Okay. Now you might think, well, that's data inefficient because you're using part of the data for the training and then part of the data for the holdout data for the evaluation. So obviously you could do cross-validation. That's much more data efficient, but it has its own issues. Okay. First of all, it doesn't really evaluate the learned rule. Okay? It actually evaluates the average performance of machine learning algorithms. So on average, machine learning algorithm will produce different learned rules based on different training data set, and it will try to evaluate the average performance of that. Right. So this, if you use, still you could use that. You could ignore this fact, the fact that the cross-validation evaluates the average performance of ML algorithm, and then you could use that to evaluate the learn rule, the specific.
Is it just me or we lost?
We lost you for a second.
Oh, really?
Yeah.
Are you good now, or?
Okay, yeah. Now I think now your connection is stable again. Can you repeat the last 3 sentences or so?
Yeah. Okay. So yeah. In addition, so this often leads to underestimation of uncertainty because the cross-validation tries to validate, evaluate the average performance of ML algorithm as opposed to the performance of the specific rule that you just learned from the data. And if you ignore that fact and then use it as a way to evaluate the learn rule, then it often leads to the underestimation of uncertainty. Okay? In addition, the cross-validation can be computationally inefficient because you have to fit the algorithm multiple times. Unlike sample splitting, which only require you to fit algorithm once. So that's where we decided to develop a new method, and we're going to call this the Cram method. It's a general methodology for simultaneous learning and evaluation. It's called Cram because it's a process of repeated training and testing. So if you never been to Cram school, I've never been, but if you have been to Cram school, that's what you do. You learn and you test, you learn and test, you learn and test. Okay? That's basically what the Cram method does. It yields, at the end of the process, it yields a single learn rule, and then also evaluates its statistical performance, empirical performance statistically. That's really the goal. It incorporates both learning and evaluation uncertainties. Okay, so why you might care about cramming, other than cramming for the exam? Cramming is data efficient. It uses entire sample to learn the decision or prediction rule. It also uses entire sample, so similar to cross-validation. It's used to evaluate the learn rule. Cramming is also computationally efficient. So this is unlike cross-validation, but similar to the sample splitting. Learning and evaluation occurs through a single pass of the sample. So there's no repeated sort of fitting of the ML algorithm, sort of separate repetition of the fitting. And as a result, you can use online fitting algorithm throughout this process. So that makes it, if such algorithm is available for your machine learning model, this makes it much more computationally efficient. I want to emphasize, although today I'm going to talk about policy learning and evaluation, this is a general methodology. Like I think there are various extensions are possible. We are exploring some, but I think the idea itself is quite general, and I think you'll see that. Yeah. So what is cramming? Okay. So cramming starts with a data set, and you will split that into several batches or many batches. Okay, so I'm going to call I'm going to use uppercase T to denote the number of batches. Okay? And for the sake of sort of simplicity, I'm going to start with the starting rule. Okay, so there may be a default rule that's currently in place or some prediction process that you already have. Okay. And then you're going to use the first batch to learn the rule 1 or update the rule 0 to get the new rule. Okay. And then you're going to use the remaining batches, the second to the teeth batches, to evaluate the performance of difference between the first rule and the rule you just learned. We're going to use this delta to denote this difference in performance. Okay. And then you're going to repeat this process. So now you're going to use the batch 1 and 2 to learn the rule 2. So that you further update the rule from 1 to rule 2. And then use the remaining batches to evaluate the difference, performance difference between rule 2 and rule 1. Okay? And you're going to repeat this all the way till the last batch. Actually, the batch right before the last one. Okay, so that's basically the cramming process. Now let me put this in the context of policy learning and evaluation, since this is a causal inference seminar. We're going to start with the data set, which is IID, and with n observation. The treatment is denoted by D. I'm going to use the binary case for the simplicity. And the outcome is denoted by Y. Okay? And the potential outcome, Y of D. And we have a bunch of pre-treatment covariates, X. Okay? We're going to make a standard assumption, the strong ignorability assumption. So we assume unconfoundedness and the overlap. Okay, so it's a standard assumption. And we're going to consider policy that we're going to run, but it could be either stochastic or deterministic. Okay, so you can have either stochastic policy, which gives you a probability of D equal 1 given the covariates, or deterministic policy where this probability is either 0 or 1. We're going to denote the value of the policy or the average performance of policy pi using the V. Okay, so this is the expected value of the outcome you would observe if you implement that policy in the real world. And again, this is allowing both the stochastic and deterministic policies. We're going to use the delta to denote the policy value difference between any two policies. Okay, and then typical policy learning would proceed by trying to find the pi such in some policy class such that this value function is maximized. All right, so that's a setting. So how does the cramming work in this setting? So here's the picture. As I said a few minutes ago, what happens is in each iteration. So here you can see iteration is on the lows. And the blue batches are used to learn policy, and the red batches are used to evaluate the policy difference between the policy you just learned and then the policy from the previous iteration. Okay, so the delta, the first iteration would be the difference between the first rule and the starting rule, and then second iteration would be evaluating using the first two batches to learn the second rule, and then evaluating the difference between pi2 hat and pi1 hat. Okay, and then you're going to repeat this all the way. Okay, so the key decomposition is this simple additive differencing decomposition. So you can basically add all the differences all the way to the last iteration, and then come up with the quantitative interest, which was the difference between the policy you end up with at the end, and then the initial policy that you started with. Okay? And notice that the last iteration, if you go all the way to iteration T, you can run the policy, but you can't evaluate because there's not much left. Okay, so we're going to be approximating that last step, and which is guaranteed to be small once we make an appropriate stabilization condition, that the algorithm is no longer changing too much at the end. Okay. Now I'm going to present everything in terms of the difference between the learn policy and the baseline policy in this talk, but you can also evaluate to just one part, like learn policy itself, without comparing to the baseline policy. Just the notation is much easier with all the deltas, using all the deltas throughout the presentation. Okay, so that's basically the cramming. I don't know, maybe I'll stop here and then see if there's any questions through the overall algorithm.
Hi, Kosuke. There are no active questions for now. And we also encourage you to propose questions as soon as you have them. Don't ask don't wait for us to ask you to submit questions.
Okay, yeah, whatever works. I'll be going through the slides. All right, so just to sort of summarize more formally, so you have a data as an input, and you have a learning algorithm that you care about, and there's a baseline policy, and then you have to determine the number of batches, total number of batches, and then the output is the estimated value difference between the learned policy, which basically takes the entire data set and put it in the algorithm, and then the baseline algorithm, baseline policy pi0. Okay, so just quickly randomly partition the data set the n into t batches. So cardi B is gonna denote each batch. We're gonna start with the baseline policy that's known, and then we'll basically iterate, learning the policy using the first t batches, and then evaluate the policy value difference between pi hat t and pi hat t minus 1 using all remaining batches, and store this result. Okay? And finally, we can evaluate the value difference between the final and the initial policy, final learned policy and baseline policy by just summing those differences up. That's our estimator. All right, so let's look at this estimator a little bit more closely. Okay, so the proposed estimator is just sum of these policy value performance differences, where the each policy value difference is basically average of t, big T minus little t unbiased estimates. So you're basically using the remaining T minus T, capital T minus lowercase t batches to estimate these unbiased differences. Okay, so there's a total of T minus T, and you're summing over the remaining batches. Okay, and each estimator is simple, say, inverse probability weighting estimator, and then you have a policy difference between the policy you just learned and the policy that you learned from a previous iteration. Okay, but using the future batches, so this cardi V is the future remaining batches to estimate these policy value differences. Okay, so these xi and di and yi come from the remaining batches and taking the average. Yeah. So it's a very simple estimator. You can use other unbiased estimator. Maybe you can do W-Boss estimator and so on. But in the paper, we just do simple IPW. Right. Now, if you look at this, it's a little bit hard to analyze because there's complex correlations across these delta hats, right? Because you're using the previous, using the earlier batches to learn, and then remaining batches to evaluate. So there's all correlations all over. So it turns out it's a little bit more easier, still challenging, but a little bit easier to analyze these if you exploit the sequential structure of cramming. Okay, so to see this, we can think of this alternative expression of the same crammed estimator. Okay, so this is the same exact crammed estimator, like the policy value difference estimator, but we're going to sum a different way. Okay, we're going to sum in the column-wise instead of row-wise. Okay, so here you can see I'm summing now from j equal 2 to t. Okay, so the idea is that we're going to use each batch and then sum over the batches, because each batch is IID once you condition on the previous batches. Okay, and so this gamma tj is an unbiased estimator of this policy difference, the policy value difference, using the batch j. Okay, by evaluating pi hat t and pi hat t minus 1. And it's easier to look at this little table that I made here. So here on the rows, you see the policy value difference that you're interested in estimating. So this first one would be difference between the first run policy and the baseline policy. The second row would be the difference between the second run policy and the first run policy. Okay. And in the columns, you see the batches and how they are evaluating. Okay. So the second batch is used to evaluate this difference, but nothing else. The third batch is used to evaluate, two of these differences, and so on. So you have this like a triangle structure. And all I'm doing is that this evaluation is being split into T-1 separate evaluation for each batch. Okay. And the policy difference between the second and third one is also split into T-2 separate batch things. Okay. And what you can do is now like you can start summing over each column, because each column is basically independent batches. Okay, so you can start on that's basically the gamma hat J. And then it'll be much easier to analyze because conditional on the previous batches, everything will be independent. So that's sort of the intuition of how we do this analysis. Now you notice that because of the triangle structure, the amount of evaluation data decreases at the rate of 1/T. Okay? T is the total number of batches, given the fixed batch size. Okay? So intuitively, that suggests that policy value difference must stabilize at least at the sort of same rate. Okay? If the algorithm is still like changing a lot, there will be a problem. Okay? So this is where the stability condition that we propose comes in. So here you see that the running algorithm satisfies the following stability rate condition, where at some point, the difference gets very small, okay? Where the T is the number of iterations. Now, this Q quantity is the expected value of this policy, like pi is a policy, okay? The round policy, pi hat. Pi hat is a round policy. So round policy difference gets smaller and smaller on average as a function of the iteration number. Okay? One thing it's important to note is that this QT is a random variable that depends on the data itself. Okay? So when we are taking expectation, we're not taking expectation over the training data. Training data is fixed. Okay? We are taking expectation over the population distribution of X, so that we are actually making assumption about the rules that we learned, given the specific training data we have. Okay? So we can relax this uniform condition to something a little bit more, less stringent. So taking the limit, and then assuming the stability condition holds in the limit. And we are, this is part where we are still learning, is that we are trying to see if there's a way to relax this. And, there may be different strategies going on. For example, here, we fix the batch size. We're not really changing the batch size. And so the question might, be like, how would you optimally change the batch size as a function of sample size, for example? Okay, so there's a lot, I think, work needs to be done to see how far we can go with this type of stability condition. But current draft has this condition. Okay. Now you might think, okay, well, who knows, the algorithm is actually satisfy this assumption. So to sort of address that, we thought about this simple algorithm to stabilize any learning algorithm. Okay. So we call this stabilizer. Well, I just came up with a name today. The sequence of batches, you have B1 to BT, and then you have some policy learning algorithm, the baseline policy, just like in the same setting. So this algorithm is going to take any kind of cramming process and then produces a sequence of policies that satisfies this particular condition. Okay, so it's actually very simple. So all we do is like a rejection step, where with the probability that decays as a function of iterations, we accept or reject the previous policy. Okay? So that allows us to guarantee that any sort of running algorithm is satisfied, the technical condition that I put out in the previous slide. Okay, so as long as you choose sufficiently large C and sufficiently small delta. In practice, we sort of find that choosing these values such that the algorithm can learn without rejection for at least 80% of the data, it's helpful. If you set it to too stringent, then the algorithm can't learn much. Okay. Other conditions. So this one is actually not a condition. It's actually a consequence of the assumption, the stability condition assumption. Basically, it says that there is a unique limit policy once you assume the stability condition. And we're going to assume that limit policy is different from the baseline policy. Okay, so if you don't learn anything, the cramming is not going to help you. Regularity conditions. We have two sets of regularity conditions. They're pretty innocuous. The one basically bounds the conditional moments. This is necessary to control these expected outcomes. And then we have moment condition for variance. The central limit theorem, you need a bounded moment, fourth moment condition. Okay, so those are the only assumptions. So you can sort of see that actually this number screwed up. So it's like it says assumption 7. It got incremented somehow. But basically the only assumption we have is the policy stabilization condition assumption. That's basically the most important assumption. Okay, with this, you can derive two basic results. One is a consistency. So the sort of get some intuition about how this consistency result come about. You can think about, okay, let's look at the estimated policy value difference between the final policy and the baseline policy. And this is the true value of that estimated difference. And let's think about how this estimation error changes over time. Basically, what you have is this missing term I alluded earlier, like the last, but if you use the entire data to learn the last final policy, you don't have any evaluation data left. Okay, so you can split this into the missing term that I denoted, and there's the estimation error of the previous policy differences. Okay? It turns out you can show, well, by assumption, the first term is basically negligible. Okay. The second term, there's a square root here. So this is just a Jensen. Is basically the sum of the conditional expected value of the conditional variances, where the conditional variance is basically conditioning on the previous batches, and then computing the variance of that inverse IPW estimator. Okay, so it turns out you can show this is bounded by this factor C is a constant, and this goes to 0. Okay, so this is why we need 1 plus delta to be there for this term to go to 0. Okay. And you can, using sort of this structure, the triangle structure, you can also show the asymptotic normality. Again, the conditional variance, some of the conditional variances come out there. Okay. So unlike the standard central limit theorem, this true value of delta depends on the data. Okay, so I really want to emphasize this because we're trying to evaluate the learned policy, not the algorithm, not the average performance of the algorithm. Okay. So this delta, the true delta, is a random variable that depends on, that's a function of the data set, training data set. And as I said, we have the way that this analysis is done is it's leveraging the fact that these deltas, the columns that I showed you, is IID conditional on the previous batches that you use to both learn and evaluate. Okay, again, the proof strategy, the blues are the data that's used to run the policy, and the red are the batches used to evaluate. And we basically have this like t to the power of 1/5, which basically depends on t, so that we look at the asymptotic regimes where the number of batches goes to infinity, while the b, the batch size, is fixed. Okay, so asymptotically, this triangle part gets smaller and smaller, and same thing on the upper triangle, relative to this square part, where we use the variation to derive the asymptotic normality. So variance estimation is also basically like using that conditional, the sum of the conditional variance structure. You can estimate this consistently. So here you see that, again, it's a standard sort of IPW type of estimator, and then taking the sort of sample variance for each batch, summing over all the remaining batches to get the estimate of the variance at each time point, each iteration at j. And this turns out to be a consistent estimate. Right. So just before I go into the simulation and empirical analysis, I want to give some my own understanding of why people should cram. Okay. So why you cramming my work is that evaluation starts early when the policy stabilizes first. Okay, so the problem of sample splitting is that if you do sample splitting in say 80-20%, you might not really need 80% to train the algorithm. Maybe the algorithm will stabilize enough if you have 40% of the data. In that case, the rest of the data should be used for evaluation to get efficient evaluation. Okay, so Cram, by doing like this train test, it basically automatically evaluates when the policy stabilizes and uses that information to do a much more efficient evaluation. Okay? In fact, the more samples used for evaluation at the early stage, right? So if you remember at the beginning, when the policy is still changing, right, algorithm is still learning, you're using a lot of data to do evaluation. So you can sort of think about like importance sampling where, where there's a lot of variability, you're using more data to run that process. You can plot these estimated policy value differences to see like how policy is actually stabilizing. Choice of batch size, we don't really have a formal answer to this. We are still learning how the cramming works. But generally, you can say that the smaller batch sizes leads to more efficient use of data because it allows you to start evaluating fast early on. Larger batch size leads to more stable policy learning. The difference from iteration to iteration, the policy won't change too much if you have large batch size. So you can say, well, noisier data, maybe you should use smaller batch size. But again, we haven't really formalized any of these intuition that we have. Okay. And here, because there's nothing for you to fix the batch size. We can also change the batch size too. Yeah, in practice, so far, we've sort of found the batch size of about 5% is give a good, reasonable performance. Okay, so let me go quickly. Or maybe I should pause here if there's any question. If not,
Hi, Kosuke, there are no active questions. Michael have been doing a great job tackling the questions.
Oh, awesome! Yeah, you get better answers from Michael probably anyway. All right, so let's see simulation studies. So we went a little crazy. So we took 2016 simulated data set. We took like all 77 DGPs. I don't know why we did that, but it was somebody's idea, maybe mine. And this simulation was, setup was designed for the estimation of conditional average streaming effect. There's lots of different specifications. So we've done a few different ones, S-runner, M-runner, causal forest, my favorite causal forest. Although it takes time to fit. For S-runner and M-runner, we use the ridge regression neural networks. And we try like 80-20, 60-40 sample splitting. Cramming, we did a 5% batch size. It's not that sensitive relative to the batch size, as long as you don't do, very different batch size. Okay, so here are the results. So comparing the cramming and sample splitting. So I don't want to, I want you to focus first on the left upper corner. So this is the improvement in the policy value. So remember, the cramming uses more data to learn than the sample splitting. So here it's 80-20 sample split. So sample splitting is using the 80% of the data. So it's, it's a lot of data, but 20% is left on the table. So you can see that the policy value actually is much, it's a small increase, but it's larger, the better learned policy under cramming. Okay, so each x-axis is simulation setup. There's 77 simulations. And here, on the B, right, the right upper corner, there's a relative change in the evaluation standard error. So this is where the cramming shines, right? Like the standard error is like 40%, 30 to 40% smaller than sample splitting. That's because it uses all the data to do the improvement. And the bias is about the same. You can sort of see the small bias that cramming has. And that's because of this like a final batch, like final learning, there's no evaluation, right? I told you that last missing term. So there is a small bias, like the blue circle has a little bit small bias. But it doesn't really affect the coverage. So compared to the standard errors, it's very small. So the coverage is pretty good in most cases. You can also look at the different sample sizes. So here, the x-axis is a different sample size. And on the left, you see that change in the policy value. Yeah, causal forest is very good, like a non-linear surface. It just does well. So doesn't need cramming. You can learn usual way. Okay. But other ones, you can sort of see that cramming has a better policy value, especially when the sample size is small. Now, standard error is actually relative improvement stays constant. So even if the sample size is large, the cramming has much smaller standard error, relative standard error. So 30-40% standard error decrease stays about the same. Okay. Lastly, we have empirical applications. So there's a clinical trial data. I don't know anything about clinical aspect of this. So, but it's a cancer drug. And we basically have binary treatment, turned into sort of binary treatment setup to just be consistent with the paper. And if you just do average treatment effect estimation, there's no statistically significant treatment effect on the survival, oral survival. Okay. But the radar analysis found that there is some heterogeneity. So it's good to do some machine learning to see if you can come up with a policy that actually treat the patients where the drug actually is effective. Okay. So we have some covariates treatment. Binary treatment outcome is the length of total survival. Baseline policy, we're going to use no treatment, treat nobody as a baseline policy. Okay. And then cramming is a 5% batch size. Sample splitting, we tried again 80-20 split. So here's the results. It turns out that both method will treat about the same proportion of people. So just above 50% of the people are being, like the algorithm tells them to treat these people. Okay. But as you can see, the estimated value under cramming is much larger than the estimated value under sample splitting. Granted that standard error is large, but this is consistent with the finding that, simulation finding where the cramming learns better. So the policy that results from the cramming is better than the sample splitting. And if you look at the estimated standard errors, it's about like 33% reduction, which is, again, consistent with the simulation results that we had. Sorry, the numbers are off. This should be 4.42, and yeah, copied wrong numbers. Okay, so that sort of shows that you can learn better, and you can evaluate better. Okay, you can also look at the learn policy and see if there's any differences. So here, I basically looked at continuous covariates and the binary covariates, and then see who the characteristics of people who are being treated under each of these methods. And what you can see actually is that the people who have stage 4 cancer, cramming, the policy and developed under cramming tells you these people should be treated a lot more than sample splitting, which it turns out to be consistent with the current clinical guideline. This trial was like a long time ago. So what we find here is again, consistent with what we currently know in the clinical studies. Okay. All right, so that's what I have. So let me conclude. So the Cram method can be used for simultaneous policy learning and evaluation. It's data efficient in that it uses the entire data set to learn and evaluate the learn policy. Okay. It's also computationally efficient because you're learning sequentially by batch. So if you have online learning algorithm, you can use that. In fact, in our simulation, like neural nets and linear regression, we used online algorithm. Otherwise you can't do 77 simulation studies. That would be too much. Okay. It's more efficient or alternative to sample splitting. And I've shown you the application to policy learning and evaluation. Okay. Now, I think the most important thing is that this evaluates the learn policy rather than an algorithm like the cross-validation does, right? So the distinction between the two is really like the purpose of your learning and evaluation. So we are excited about cramming, and we've been cramming away. And so there are some evaluation extensions that we are currently working on. Like bandit is one obvious sort of candidate because there's this sequential structure that I told you about. So it seems that cramming is a good candidate for that. Active learning is, I think, another application that would be super useful because the sample size efficiency kind of consideration is very important there. And then obviously, more general sort of machine learning prediction and classification as opposed to policy learning would be of interest. And some people suggested, well, why don't you cram cross-validation or cross-validate the cram? So we are also considering that possibility to combine, especially for machine learning prediction and classification. We are thinking how we can combine these ideas for different purposes. So I'll stop here.
Awesome. Thank you for the very nice talk. I think in the interest of time, we should switch over to discussion. If there are any remaining questions after that, we can discuss them after that. So yeah, for the discussion, we have Rui Song. Yeah, feel free to start whenever you're ready.
Can you see my screen now?
Yep.
Great, let me get started. Well, thanks, Kosuke, for the very clear presentation, and I really enjoyed reading your paper. So I wanted to discuss further about your extension in the last page. So I'm currently a senior principal scientist at Amazon, and Henry Tsai, who is also a panelist today. So we're going to just discuss this paper. So this is a recap of the paper. Essentially, for different iterations, the data are split into T batches with the blue part, the batches in the blue part, the policy learning is performed. And then with the red batch, policy evaluation is performed. Then at each iteration, the estimator for the value difference of a pi t hat minus that pi t minus 1 hat is calculated. Then near the end, this estimator delta hat are summed together as an overall value difference estimator. So, so in summary, Cram paper method has a nice performance. So in terms of the comparison with sample splitting plus cross-validation, and the last paper is my paper where we have a similar idea, but we apply this idea for reinforcement learning in infinite horizon settings. So, so here the table lists the comparison of those 4 methods in terms of how do they use the full sample, and also if they produce one policy or not. So it turns out like Cram and sample splitting plus cross validation, our SAVE method both use full sample. In contrast, sample splitting is not sample efficient in the sense that they do not use full sample. And also in terms of the final results, so both also Cram sample splitting and our SAVE method can all produce one final policy value estimation. So here is a general description of our procedure in the SAVE method. This paper appeared in JSSB 2022. I also want to mention that we have an earlier paper that deal with the value estimation for single stage setting with similar idea. That paper was published earlier in GMLR. So without a detailed introduction on the notation, you can consider this is just infinite horizon setting of the setting Kosuke described at the beginning. At each stage, you're going to have a state or covariance action, which is your treatment, and reward, which is the outcome. And you're going to have T stages. So for infinite horizon, T can be very large. And in theoretical framework, T can go to infinity. So here we have 2 dimensions. Dimension of T, the time, the horizon, and also dimension of and the sample size. That's why we divide the data into Kn, that's in the sample size dimension, and the Kt, that's in the time horizon dimension. And so we divided the data into Kn times Kt blocks, and then the idea is for those blocks, we're going to use the first case block of data to estimate the optimal policy, and use the remaining blocks of data to do the value evaluation. And in the last step, we derive the final estimator as a weighted average of all the previous K-1 value estimators. So here you see we have like 2 dimensions. So in the dimension of a sample size of the subjects, you can certainly permute them because we assume the subjects are independent, but across time, you're not able to permute it because there's a dependency across observation, because the current observation will have a dependency on the past observation. Let's just use a plot to illustrate the idea. So that's what I referred to. We have like the time dimension and also the sample size dimension. So from the first block, we estimate the optimal policy, use the first block of data, and then evaluate the value using the second block of the data. And then we estimate the optimal policy, use the first 2 blocks of data, and then evaluate the value, use the third blocks of data, and so on. Estimate the optimal policy, use the first 3 blocks of data, then evaluate, use the last blocks of data. And then we take the weighted average of the evaluation of the T+1 block of the data as a final value estimator. So in this GRSSP paper, we did derive the asymptotic normality of the value estimation. Also in that paper, so you can see the setting, we evaluated the estimated optimal policy based on offline data. That is, all the data are available. We actually also develop another type of data that's online learning, in online reinforcement learning. That is, you're going to collect the data and your policy, behavior policy can change over time. Your data collection policy can change over time. So here are just some discussion points. So we can see there are certain similarities between Cram and Save. Certainly in terms of the setting, in terms of implementation, there are some differences. So it's interesting to compare them. And also in terms of value evaluation, I think Kosuke also mentioned some discussion about the efficiency improvement. So I wonder maybe weighted average could provide some new idea for improve the efficiency. And also here, as the nature of reinforcement learning, when you have infinite horizon, you're going to naturally have the dependency across time. I think Cram is a very general framework. In the current one-stage setting, it may not be an issue, but if you want to further extend to Bandits or some other online RL, that should be something you may need to consider. So that's the first work. Next, I wanted to just talk about another related work. That's a joint work with Henry, who is a panelist here. So this is this slide is about a general overview on the offline policy evaluation. That is, we're going to have offline data, and we wanted to estimate the expected outcome used under a target policy, which is possibly different from the behavior policy, where you use this behavior policy to collect the data. So in terms of the next setting, that's the online setting. That is, we're collecting the data, and this policy certainly can change over time. And this is close to what Kosuke mentioned, the Bandit setting. So we develop a method, we call it doubly robust interval estimation, in short as DREAM, to deal with this Bandit setting. In particular, we consider three popular methods: Ipson-Grady, Thompson sampling, and UCB in this paper. So here are some discussion points for the comparison of a DREAM, this paper, where we provide the whole statistical inference with Cram. So again, in online learning, the data are not IID. You can certainly see the data dependency. So even though it's bandits, you're not going to have so the state for each time points are independent. However, the current state will depend on the policy, and this policy could depend on the past history. Therefore, there's such a dependency. So it will be interesting to consider how to extend the general idea of a Cram into this non-IID setting. And also, the optimal policy needs to be estimated and updated in real time. So a natural question is, how can we make sure the stability policy assumptions still hold in online setting? So for my understanding, the stability assumption in Kosuke's work may be related with, first of all, the choice of a batch size, which is something discussed in the literature for batch bandits. And also, that may also depend on the convergence rate, the performance of the estimator itself. So I think that's worth to be further discussed. Another important issue is about the exploration and exploitation trade-off, which is an important feature for online learning. So how can incorporate this trade-off in Cram is something critical. So in our DREAM paper, one of our major contribution is to somehow weight this exploration probability in our value estimation, and how to quantify this weight and quantify its contribution to the final inference is an important and challenging task. I think I will stop here. Are there any questions, comments?
Yeah, thanks for the nice discussion. Yeah, Kosuke, if you want to respond, feel free to say a few words.
Yeah, thank you. Yeah, I'm a little embarrassed that I didn't see your papers before, so I'll definitely check those papers out because it's clearly very closely related. So thank you, and if you have yeah, if you can send me slides, that'd be
Definitely.
amazing too.
I will
Yeah,
share with
yeah.
you the slides and also the
Yeah,
three.
yeah.
I talked to
And then
two.
we can.
Here's the earlier paper
Okay.
idea for one stage setting. Yes.
Yeah, and then we can definitely talk more offline about these issues that you raised, which I think are important. And we've done some exploration, but don't quite have as much as you've done. So yeah, thank you.
Mathematical-wise, I think they share similarity because I checked your proof. It's also based on martingale type of results. So I do think the nature of the problem are very similar, if not the same.
Right.
Awesome, thank you. I think Michael Lee has tackled all the questions in Q&A or is currently tackling the last one. So
yeah, Michael, you should say something. I think you should.
Yeah. So I think sorry, I was just typing away on the question. No, I think Ray, thank you for your discussion. I think we'll look into the paper. My understanding is that the conditions, because the conditions and the settings are different, the assumptions that you raise, like A1 to A5 in your proof, and I've only taken a very brief scan, so please forgive if my misunderstanding is relatively quite different to our stability conditions raised in our setting. And
which paper did you
we're talking about the statistical inference of the value function for reinforcement learning in infinite horizon settings.
Okay.
Like if we and I don't want to sort of necessarily go into necessary specific details, but I think that there is a tail condition that is required for the safe method to work, and I'm not sure how it would translate into our setting, and I'm in particular the theorem 3, which says that the following event occurs with at least probability 1 minus O to the 1 to the negative K for any finite K greater than 0. I'm not exactly sure because clearly I'm not an expert yet, and I will look into more detail, but I think it will definitely be an interesting comparison to understand how Cram works. First of all, how Cram can work in a non-IID setting, and how how the safe method would translate into an IID setting, and what kind of results will be like. Because even though that we do utilize martingale theory, the standard martingale theory of just conditioning on the past samples was not enough for us to was not nearly enough for us to get our results, and we had to. So we'll look into closely detail about the similarities and the differences between Cram and safe.
Definitely. Yeah, let's definitely follow up offline because we don't have enough time to finish all the discussion. I want to point out the theory and assumption, there may be components of the specifics for Q-learning. We may tease them out because the general principle may be more just not only restricted to Q-learning specific structure.
Yeah, completely agree. Which is why I think that we need to read the paper more closely than a quick scan. So
sounds good.
Awesome. Thank you so much. I think it's time to wrap up. So first, thank you so much, Kosuke, for a very interesting talk, and Rui for a very nice discussion. Also, thank you, Michael Lee and Hengui Chai for joining today. Next time, we're going to have Chao Ma from Microsoft Research, who will talk about towards causal foundation models on duality between causal inference and attention. We're all looking forward to that. Hope you have a great week, and see you next time. Thank you.
Great. Thanks, everybody.
Thank you.
bye.
Bye.